Uh, Coming back to the convection diffusion equation, uh, last time I have uh, discussed the approximation of derivative by several mechanisms based on polynomial basis and exponential basis, trigonometric basis. So I mean to say there can be several formula for uh, discretizing first order derivative, and in the same way higher order derivatives can be obtained. Here we will implement all those formula for solving convection diffusion equation in the general sense. So we take a convection diffusion model, which is epsilon, and u double prime stands for second derivative of u with respect to x, equal to ax u prime x plus bx ux plus gx. X is in the domain, one dimensional domain. Epsilon is certainly positive, but it is a small quantity, and u is specified at left end and right end. Here ux is pollution concentration at a distance x. U superscript written x, that is u prime, so that is the u first derivative, that is convection, and second derivative of u is diffusion. Epsilon is diffusivity, a is velocity in of pollution, bx is convection coefficient, and gx is source and sinks. So this is what one of an example of this source and sink is. For example, if we burn methane, destruction of methane and oxygen, that will be contributing towards sink, and creation of carbon dioxide and water vapor will constitute to the source. Now, uh, why we need mathematical analysis of such kind of equation? Just a simple example. Suppose epsilon u double prime is equal to u prime minus 1. This is a very simple second order linear differential equation. X is given in the domain 0 to 1, and u at 0 and u at 1 is specified as 0. So if we take epsilon is equal to 0, that is epsilon is very close to 0, then what happens? This equation is basically u prime x equal to 1, and the solution of this, along with the condition u0 is 0 and u1 is 0, has no solution. So I mean to say, when epsilon is very small, the solution of equation 3 is badly behaved. Such type of equation is called singularly perturbed. Well, just for explanation purpose, I have directly substituted epsilon equal to 0. But what happens when we are using finite machine, that is when we are implementing it in the algorithm, and epsilon is taken to be very small. Suppose epsilon is taken as 10 raised to the power minus 5, and our computing facility, I restrict the computing facility that it will calculate only up to 3 digits after decimal, just for an example understanding purpose. Then 10 raised to the power minus 5 will be basically 0 for computing purpose. For finite machine, this machine has always finite memory and finite space. So that is why in that case, this type of equations will behave badly. That is why, despite availability of theoretical solution, analytical solution, numerical solutions play a very important role. That is why I have written there are two situations. Number one, in many nonlinear ordinary differential equation or nonlinear partial differential equations, exact solutions are not known. Then you require numerical solution or approximate solution. And sometimes even the known analytical solution, when behaves badly, then we need numerical treatment. Next, computational mechanism for the non-linear stationary convection diffusion equation. I have taken this here, a general formulation of nonlinear equation, second order, boundary value equation. So it is epsilon u double prime equal to function of x, u and u prime. Boundary data is specified. U at lowercase a is a and u at lowercase b is uppercase b. So our domain is from A to B. We divide it into a set of mesh points, and that I'm going to denote it by x0, x1, x2 up to xl plus 1 equal to B. The last node, the last mesh point is basically B, and initial mesh point is A. All are equally spaced. So here what happens, the next node xl plus 1 is basically xl plus h, and h is b minus a by l plus 1. We shall denote u subscript l, which is equal to u at xl, as the approximate solution value at the mesh point xl. Now I am going to define two operators. One of them is A is curly and curly B operators. A is defined as half of ux plus h minus u of x minus h, and bux is ux plus h minus twice of ux plus ux minus h. The second one is second central difference operator, exactly same as second central difference operator, and the classical notation for it is delta square. So delta square in this case is B. I have chosen different notation, curly A and curly B, because later on we are going to implement non-polynomial basis, and there the symbol delta is not used. Therefore we have configured this another operator, another symbols. So in this with this definition, if I expand it with the help of Taylor series, 1 by h operator a u is coming out to be u first derivative plus order h square, and 1 by h square bu is coming out to be u second derivative plus order h square. So if we ignore the h square terms, then these two formula is basically is giving you the approximation of first and second order derivative. We can apply it in a computer program. So if we substitute these operators in the given equation, our given equation is epsilon u double prime equal to function of x, u and u prime. So here for u double prime, I have substituted bu by h square. Epsilon is as usual multiplied equal to function of x. This is evaluation at a point xl. So at x equal to xl, this becomes xl. U at xl becomes ul, and first derivative is 1 by h aul. So this is a very simple finite difference replacement of the nonlinear equation. It is of order h square. Now the most important is in this formulation, only 3 points are used, and it can be it can gives you a tridiagonal matrix, tridiagonal Jacobian for the iteration. And for a nonlinear system, either we apply Newton-Raphson method, or we apply Gauss-Seidel method or Gauss-Jacobi method, whatever feels suitable after incorporating this boundary data. Well, the most important is this is order h square here. This scheme, this method for solving nonlinear equation is second order accurate. In the previous example, in my last lecture, I have shown that a first order method, a second order method. So if we use second order method, that gives more accuracy in a less computing time and a small number of mesh points. So the same way, on the same line, we are going to enhance this local truncation error order h square up to order h4 for the differential equation. And subsequently, it extends to the partial differential equation of elliptic type, parabolic type, hyperbolic type, and so on. Now, so before solving most general form of linear equation, nonlinear equation, uh, to begin with, I have taken a most simplest form, that is epsilon u double prime equal to gx. This is the easiest equation, second order equation, where the right hand side is only function of x. And we will develop a high order scheme for this second order equation, non-homogeneous second order equation. And based on that formula, we extend that scheme to obtain high order formula for the nonlinear problems. So this is for understanding purpose. Now at the point xl, this equation is written as epsilon u double prime ul equal to zl. Now I am going to formulate a linear combination. It is h square gl plus h alpha gl prime plus h square beta gl double prime. Now this I have simply stored it in chi xl. I have denoted it in chi xl. Right hand side is important, where alpha and beta in equation 3 are parameters whose values needs to be determined in such a manner that we achieve a high order method. Now, uh, use this operator B in equation 3. We get operator B. So we get here epsilon BUL plus alpha epsilon HQ UL triple prime plus epsilon H4 by 12, 12 beta minus 1 U4 plus order H6. Here it is G and here I am getting U. How does it happen? Oh, very easy. This G is basically epsilon U second derivative. So in place of G, U second derivative into epsilon will appear. In place of G first derivative, epsilon U third derivative will appear, and so on. So basically, all the expressions will appear in terms of U. Here, here the first term consists of an operator. Second and third terms are appearing with third and fourth order ordinary derivative, and the last term is order h6. If I choose alpha to be 0 and beta to be 1 by 12, that is, I have not chosen. Basically, I am going to equate the coefficient of third order derivative of u and fourth order derivative of u to 0. We can have alpha is 0 and beta is 1 by 12. That is, for this value of alpha and beta, equation 4 will appear with this operator B and order h6 terms only. This is what we are trying to achieve. Now, for this value of alpha is 0 and beta equal to 12, equation 3 becomes h square gl plus 1 by 12 h square g double prime plus order h6. Now, what is G double prime? I have defined operator B on U the same way operator B can be defined on G. So G double prime is 1 by H square BGL, and that is order H square. Substitute it, we will get epsilon BUL equal to H square GL plus 1 by 12 BGL plus order H6. Now just put put the detailed expression of operator B and detailed expression of BGL. We are getting equation 7 as a scheme which is giving us local truncation error order H6. Please note that I have started the formulation. Just a moment. Just a moment. I have started the formulation here in equation 3 by taking h square. The linear combination started with multiplication of h square. So the final scheme here in equation 6, we must have to divide throughout by h square. So here it is order h6. So when we divide throughout by h square, the right hand side is coming out to be order h4. So the actual truncation error is order h4, and that is the order of the scheme. That is why it is fourth order scheme. This is basically Numerov scheme for solving second order linear equation. Now, there is a question why I have multiplied here in by h square in this equation 3. Why I have multiplied by h square? This h square multiplication is just for simplicity in deriving the scheme. That's all. Now, what is this equation 7 is giving us lots many things from this. Listen, what happens? It involves only three nodes, L minus 1, L, and L plus 1. So, when we write it in the matrix form, in the matrix only three diagonals will appear. One is main diagonal, another is subdiagonal, that is a diagonal below the main diagonal, and one diagonal above the main diagonal, that is super diagonal. So only three diagonals, so that will classified in a tridiagonal matrix. Moreover, it uses only 3 points, therefore boundary points can be easily incorporated, right? So we call it compact scheme. Compact means I have a second order equation, and at most we require three mesh points to discretize the second order derivative. Second order derivative is the highest order derivative present in our boundary value problem. That is why the minimum number of points, that is 3, required to discretize the highest order differential in the equation is 3 only. Therefore, considering only 3 mesh points will suffice to obtain a fourth order method. It doesn't mean that with the application by consideration of 5 mesh points, we do not get a scheme. Yes, we get a scheme by incorporating 5 points, 7 points, 9 points, as many you wish you can, but by taking more than 3 points, it requires fictitious points, and we are having difficulties in taking fictitious points because we don't have information beyond the given domain. That is why we restrict it up to only 3 points. So this is what I have written concisely here. It uses the minimum number of mesh points required to discretize the highest order derivative present in the model. Thus, it is compact and needs smaller computing time for practical application. Here it is one dimensional problem. In the same way, if we proceed to uh, second in two dimension, so suppose that we have a Poisson equation del 2u by del x square plus del 2u by del y square equal to function of x comma y, a Poisson equation. So I will we are having a domain like a square, 0 to 1 and 0 to 1 x and y varying. So in that case, I will take 3 points in x line and 3 points on y line. So in total, we are having 3 into 3, that is 9 points will appear for our consideration. So in one dimension, it is 3. In two dimension, it is 3 into 3, that is 9. Same way, if you proceed to 3 dimension, it is 3 into 3 into 3. So 29 points will appear in the formulation. In fact, only 19 points are required in three-dimensional problem, but 27 points will somewhere in your in the picture. Just imagine if we are considering multi-dimensional problem, how much points are required to discretize a equation, a multi-dimensional partial differential equation. That is why if we increase the number of nodes in for computation for one dimension or two dimension, there is not much difficulties in computing purpose, but for three dimensional problem or for higher dimensional problem, there is a problem of computing time. It takes huge time to solve a simple nonlinear equations kind of sine Jordan elliptic sine Jordan equation. So the main challenge is to develop the solution technique which requires as minimum as possible, develop the scheme which requires minimum CPU time. That is, any method which requires less computing time is welcome in this area. Now here I will expand the previous scheme to the general form, that is epsilon u double prime equal to function of x, u and u derivative. Because in this equation 8, we have an involvement of u derivative and the formula, what we have derived here, it is gl minus 1 requires, the formula requires gl minus 1 gl and gl plus 1. So if there is a straight line, and on the straight line if we put suppose this is the straight line and I am putting this middle one is l, this is l plus 1 and this is l minus 1. So uh, uh, so in case of nonlinear equation u derivative, I require u derivative at this point, at l plus 1, at l and at l minus 1. This is what I have written. U prime, that is u derivative at l, is this formula. ul plus 1 is this one, and ul minus 1 is 1 by 2h minus 3 ul plus 1 plus 4 ul minus 3 ul minus 1. So these three formula are the formula for first order derivative at three different nodal points, that is xl, xl plus 1 and xl minus 1. Now the question is, the first one is already known to all of you. The second and third formula, how to calculate it? How I have got the coefficient as 3 or minus 4 or like this? Very easy. Just take a linear combination of ul plus 1 and ul minus 1 and just expand the Taylor series. You will get the values of the coefficient which approximate first derivative at l plus 1 and l minus 1. Now, with availability of these values, I am going to define g cap at l plus minus 1 as g of x l plus minus 1, u at l plus minus 1, and u derivative cap at L plus minus 1. So basically there are two evaluations here. So I have two things, GL plus minus 1 cap. With this availability, I am going to update the first order derivative at the central point, that is at XL, by the relation u double cap prime equal to u single cap prime plus h a gl plus 1 cap plus b gl minus 1. A and b at this moment is not known to us. This is just a parameter. So that later on, when we expand our scheme, we need to determine values of A and B in such a way that leads to the higher order scheme. Now, then define G double cap as G of XL, UL, and U double cap prime here as defined here. And the compact scheme, which is epsilon B UL equal to H square. This is same as previous one, except G is basically here G cap L minus 1, G double cap L, and here I forgot to write here, it is also G cap L plus 1. So G is basically updated. So the right hand side here is, right hand side is G in this case, which is a function of X, U and U prime. There it was only X. So we basically need to update G, that is right hand side needs to be updated. Now when we put these values in this scheme in equation 9, then we realize that if you take b equal to minus a and a equal to minus 1 by 20 epsilon, it is coming out to be 6 local truncation of order H6. Now, I have not written here the derivation because it is exactly same as what has been done earlier. So we have got as a result is fourth order scheme, fourth order, because if we divide both side by H square, left hand side becomes epsilon into u derivative in the limiting case. That is why I am dividing both side by H square. So this is giving us a fourth order scheme for the value of a and b specified here for the singularly perturbed second order equation. Now, how to derive it? Very easy. With the help of Maple program, I have illustrated these things so that calculations can be done in an effective manner. I have denoted by x naught as x, x1 as x naught plus h, and x2 as x naught minus h. U is u at x naught, u1 is u at x1, and u2 is u at x2. Now, just formulate a linear combination A u naught plus B u1 plus C u2 and find the difference between T and H du at x naught. That is, I am finding approximation at the central mesh point, that is x naught, that is x, and just expand it with the help of Taylor series and then convert it into polynomial and then collect all the derivative terms, make it factor. You will get values as this. You will get three equations, solve it, you will get a, b, c as this. So with this value of a, b, c, I will put it in this t, to write OPX, that is operator A, what has been defined in the text, that is half u at xl plus 1 minus u at xl minus 1. So this is in Maple, the operator A is difficult to write. That is why I have written OPX, that is operator X. Now, same way, The another operator, that is del x, that is delta 2x, that is operator b, is defined as minus is obtained as, I should not say defined as, it is obtained as minus 2 u naught plus u1 plus u2. This is again same as the second central difference operator. So these are the two operators, and the notations are same as I have written this u1 x0, that is derivative of u at x naught. Next one is derivative of u at x1 and derivative of u at x2 as this formula. And this is u2 x0 means u second derivative of x at the point 0 is coming out to be 2 u naught with minus sign plus u1 plus u2 whole divided by h square. So this is basically again the second central difference replacement divided by h square. When we expand this OPX and del x, we are getting first derivative into h plus order h cube, second derivative into h square plus order h4. So this is basically giving us first and second derivative. Now consider g in text is here f for maple. So here fx is taken as epsilon into second derivative. I will write f0 as fx, f1 as first derivative, f2 as second derivative of f. Second derivative of f means epsilon into fourth derivative of u. So everything is actually coming in terms of u. Now take a linear combination. H square p naught into f0 plus h into p1 f1 plus h square into p2 f2. In this linear combination, we are having two operators. One is OPX, that is operator A. Another of them is operator del x, that is operator B. Now, with the help of this operator A and B, that is with the help of operator OPX and del x, we will replace the first derivative and second derivative in terms of operators. So this second derivative is written as in terms of del x. Basically, I am writing del x equal to second derivative. Just from this equation, find the value of second derivative and write everything in terms of operator, that is del x. Here, OPX or first derivative is not written because the coefficient of first derivative here, this f1, coefficient of f1 is basically coming out to be 0. So just ease the calculation, I have not written OPX. But in case of variable mess or higher or other higher order method, you have to consider other operators also. Now, after substituting and expanding it with the help of Taylor series and collecting all the terms of del x, we will get it as t2 equal to epsilon d3 derivative, third derivative p1 hq minus this coefficient h4 plus epsilon delta x p naught. Now, we intend to remove all the terms except operator terms. So here operator terms is this epsilon into delta x p naught. Keep it. Try to equate to 0 all other terms, coefficient of all the other terms. So here p1 is 0, coefficient of third derivative is 0, means p1 is 0, p1 is 0, and coefficient of d4, that is h4, is coming out to be minus 12 p2 plus p naught is coming out to be this. So I have got value of p1 and p2. p1 is 0, no problem, but the value of p2 is coming out in terms of p naught. Now, what is the value of p naught? Listen, if we take, for simplicity, if we take p naught is 0, then what will happen? Very interesting. Listen here in this equation, if we take p naught is 0, then this P naught 0, P1 is already 0, and P2 is appearing in terms of P naught, so that is also 0. The whole linear combination collapsed. So we must take some non-zero value. Any non-zero value, any non-zero real value will suffice our purpose, and that gives same order scheme. Maybe for simplicity we can take P not equal to 1. So here for ease in calculation I have taken P naught is 1, P1 is 0, and P2 is 1 by 12 P naught. Then T2 is coming out to be this. Now again I have started with T naught equal to H square P naught F0 plus H P1 F1 plus H square P2 F2. What is this F naught F1 F2? F naught is Fx. F1 is first derivative of F, right? And F2 is second derivative of F. So if I write F naught equal to Gx, just for understanding purpose, then F1 is first derivative of Gx, and first derivative of Gx is 1 by 2 G1 by H minus 1 by 2 G2 by H. Second derivative of F is coming out to be minus 2 G naught. This is B operator on G is coming out to be this. Put it here, you will get this one, equation 20. Equation 20 is exactly same as what we have obtained in the theoretical text, that is minus epsilon operator B U equal to H square by 12 10 G naught plus G1 plus G2 plus order at 6. So here this scheme is basically the fourth order scheme for solving equation. Now this is the previous one. This scheme we can find the truncation error. Nothing to do, simply expand T with the help of Taylor series. We will get it this sixth at 6. So by this way we can find the local truncation error in an efficient manner. Well, in one dimension the calculations is simple. For uniformness the calculation is simple, fine, we can do manually. But in case we are moving to higher dimension for irregular meshes or irregular domain, then calculation is very vast, and then we must rely on some available tools like Mathematica, Maple, MATLAB, whatever. Now this is the derivation for Maple derivation for the simplest form of equation. Now we will extend it again to the general equation. Now as usual, here I have put these three things in the comment line. Again u0, u1, u2 and x0, x1 and x2 is exactly same as what has been defined earlier. And I will write u1 x0 bar as like this minus first derivative I have written as here u1 x0, and here it is u1 x0 bar, the updated one. Like this, expand it in a Taylor series, you will get this final scheme. And these are the derivations. I hope you can understand it. This code written in a most easiest manner. Finally, when we apply the algorithm, what has been discussed, we are getting this one. Now, in this last, our aim is to reduce this scheme up to order H6. So if I take B equal to -1, most of the terms will vanish out. So we are left with only this one. And in this term, coefficient of H4 here, it is 20 A epsilon plus 1. If we solve it for A is coming out to be -1 by 20 epsilon. This is what same as what we have obtained earlier. For this value of A, that is if we are putting A equal to -1 by 20, this TT is coming out to be something into H raised to the power 6. This is the local truncation error of the scheme. So by this way, we have got the scheme for nonlinear equation. Now, numerical simulation, I am going to consider, just a moment. Yeah, numerical simulation. Is it visible to you all? Okay, so this is minus d2y dx square plus lambda dy by dx plus y minus 1. Let me expand it. It is then looks more clear. Yeah, this here lambda, if we take if we write in place of lambda, if we take 1 by epsilon, so it is coming out to be the same form. So it is coming out to be this. It has analytical solution this, but the solution changes sharply by changing values of lambda. Now here I have taken lambda equal to 100. Please note that I have told you lambda is 1 by epsilon. So if lambda is 100, then epsilon will become 1 by 100. Similarly, when lambda is 1000, epsilon will become 1 by 1000. So epsilon is going to be, take epsilon in a diminishing value. So if you take lambda equal to 100, the L infinity error is coming out to be -3, -4, -5 for 10, 20, 40 number of nodes. And the order is coming out to be 3.8, 3.9 for L infinity error. And similarly, L2 error is coming out to be 5.6 minus 3, 2.16 minus 0.4, 1.23 minus 5. It is also coming out to be 4.7, 4.1. If we again increase the value of lambda, that is, if we decrease the value of epsilon, it is coming out to be, for the same number of mesh points, 10, 20, 40, 80, it is coming out to be 1, 3, minus 4, 5. Error is almost close to 4. Here also error is almost close to 4 in both the cases, L infinity norm and L2 norm. So this is what we have got finally, that a fourth order scheme for solving nonlinear singularly perturbed problem is beneficial in terms of order and accuracy of the scheme. So I just suggest, based on this, we can have examples of other problems. We can formulate the different types of a scheme based on non-polynomial basis, and many more things can be done with the help of this base derivations. With this, I am stopping here and will continue in the next class. Uh, Thank you. Thank you very much.